Great. What we're going to do today is to see how an abstract category imitates the category of sets. And it's important to see that because, in fact, we will later find out that any category can be seen as a piece of the category of sets. So one can think of the category of sets as being some kind of universal category in which all categories reside. But with a remark that the size of those categories must be small enough. As you know, in set theory, there is issue of size. For instance, if I take the category of vector spaces, let's say, the collection of vector spaces is quite big. It is not a set. Due to issues like Russell's paradox, not everything is a set. And so we can't make the category of vector spaces live completely inside the category of sets, but we could also consider a larger category, the category of classes of sets, and then we can fit them. So up to size issues, every category can be fitted to live inside the category of sets. So the category of sets is then an important guide to studying categories. And maybe before we talk about things called generalized elements, which is the topic for today's lecture, let us first say a few things, as I said before, about the category of sets. So in the category of sets, which we write as set, this is the category of sets. Objects are sorry about that. Objects are sets, and morphisms are functions between sets. I'm very sorry, just one moment. I need to take an urgent call. Sorry about that. I'll be back in a minute. I'm back. So objects are sets, and morphisms are functions between sets. So if I have two sets, x and y, a morphism from x to y is a function from x to y. And by a function, we mean what one means in set theory. So in formal language, we can think of it as a subset of the Cartesian product, so which identifies the pairs x, y, where x maps to y. And the condition is that for every x in x, there must exist a unique y in y, such that the pair xy belongs to f. And then there is notation we use where we write that unique y that exists for a given x, we write it as f of x. Can I maybe suggest that you don't do anything with your cursor while you're not writing on the board, so that your cursor doesn't move around over the text, if that's possible? Okay, so it's important to give a definition of a function, because since we want to know the exact shape of a category, we want to know very precisely what the morphisms do, and sometimes also how many of them there are, and so on. And so with a precise definition, we will always be able to check exactly whether there is a morphism or there isn't, and if there is, which ones there are, and so on. Composition in this category is defined as the composition of functions. So I'll say it's the usual one. Let me, for the completeness sake, let me write out nevertheless the formula for the composite. So this is now very similar to the category of natural numbers we had, where objects were numbers and morphisms were functions. So composition is defined by this formula. And then it's easy to see that it's actually associative and the identity morphisms are there, so everything is fine. We already know from the previous lecture that in this category, let's formulate this as a little theorem. In this category, the terminal object is given by a single element set. So a set with just one element is a terminal object in this category. And we're now going to make use of this fact. By the way, just a remark, as we know already, any two terminal objects are always isomorphic, and we also remarked previously that if I have an object that's isomorphic to the terminal object, then that object will also be terminal. So we can strengthen this theorem and say that terminal objects in the category of sets are exactly the single element sets, since being bijective to one specific single element set means that your set has exactly one element. So moreover, terminal objects set are single element sets. And now we will see how the single element set, so in short, we call, in set theory, we call such a thing a singleton, how it can classify elements of all the other sets. If I have a set X and I have a single element set, what do you think should I do in the language of the category of sets to identify a particular element in the set X? It's a question, feel free to answer.
I'm not entirely sure, but can you combine the singleton with itself and like map that to each element, almost like you do with the natural numbers?
What do you mean when you say? What do you mean when you say combine the singleton with itself?
You create sets of singleton sets, essentially.
Well, that we don't know how to do in a category, right? So we want to use just the language of the category, nothing else.
Okay. Yeah, I'm not sure.
So all we have in the language of a category thus far is we can talk about objects, we can talk about morphisms, we can talk about composition. Do any of these ingredients give us a way of identifying elements in the set X? Making use of the singleton, which we can talk about in the language of a category because singletons are terminal objects. So we can just think of this left-hand side here as a terminal object in the category. And is there a way of now using the terminal object to speak about elements of X? We can't speak about elements of X directly because we don't have a notion of an element in a category, but maybe we can access them indirectly through whatever we have in a category. So this is an important question because the whole philosophy of category theory is to take existing knowledge, whether it's mathematical or not, in this case, we are talking about mathematics, and see what is the best way of looking at it through the language of categories, because when you do that, then it becomes accessible to other fields as well. The ideas become accessible and kind of build bridges across fields once things are formulated in the language of a category. So it's important to develop an intuition how we can take an existing phenomenon and rephrase it in the language of categories. And here we have one simple example of that. Can we rephrase the idea of an element of a set in the language of a category once we're viewing the category of sets?
The only idea that I kind of have is if you use a morphism, and maybe since you have since your morphism is defined that it maps to a unique element in another thing, you can maybe use that.
Fantastic, Matt. Yeah, that's a great idea. That's also the one I know how this can be done. So if I consider a morphism from the terminal object to X, as you already said, because a morphism must map everything in the domain to a unique element in the codomain, it will identify a unique element in X, namely, if this morphism is F, then the element that it will identify will be F of the star. And moreover, every element in X will be reachable this way because for any element in X, we can consider the function that maps star to that element, right? So we have this bijection between hom star X, which is the set of all morphisms from the singleton to X, and X itself. It's quite a fascinating bijection, this one, because this thing is a set that is accessible in the language of a category, where this set is not accessible as a set in the language of a category, because in the language of a category, X is just an object. So when we abstract away from the category of sets to a general category, we won't have X as a set anymore, but we can think of that set in terms of this hom set. And that's pretty much the idea of generalized element. So a generalized element of an object will be a morphism to that object. And so far, our generalized elements have domain the terminal object, but that can be dropped as well. So let me write down the definition. Generalized element of an object X is a morphism F from C to X, where C is some fixed object. In the previous example, we fixed the singleton set, but we could have also fixed any other set. Of course, in the category of sets, if instead of the singleton we take some other set, functions from that set to X will no longer be just elements of X, right? And that's why this concept is called generalized element, and it's not an element. Now let's see that, in fact, this concept matches quite nicely with how product of two objects is defined. If we recall from one of the previous lectures, when I've got two objects, X and Y, their product is an object together with a pair of morphisms, right? So we have here pi1 and pi2. And then the property says, the defining property for a product, so this is the structure of a product, but there's also an axiom. And the axiom says that for every object C, and now I'm deliberately using the letter C there, maybe we did that already the previous time, to kind of give you a hint of what I'm going to say afterwards. So for any object C and for any morphism F and for any morphism G, there is a unique morphism here that makes the triangle commutative. And we already said that the uniqueness of this middle map can be rephrased as hom Cx cross Y being bijective to hom Cx cross hom Cy. We made use of this bijection as well because we agreed to write H. Maybe we didn't emphasize that well enough, but H can be written as a column vector consisting of F and G, or sometimes we can also write it as a row vector. We have to agree for the orientation once and then stick to it. Remember that there is also sum and a similar property that defines a sum. And for sum, it has to be transpose of whatever we agree on for the product. And that has to do with the fact that in the category of matrices, the way we define sums and products, the idea of transpose came into play there. So to say that for every F and G there is unique H, which makes those two triangles commutative, is the same as to say that this canonical map from hom Cx cross Y that maps an H to the composite pi1H and pi2H, that this canonical map is a bijection. So first of all, okay, so why is this so? Because to say that the function is a bijection, right, is the same as to say that for anything in the codomain of the function, there is a unique element in the domain mapping to that element. If I have two sets and a function between them, one way of expressing that it's a bijection, once I already know I've got a function between the two sets, is to say that for anything in the codomain, there must be a unique thing here that maps there. And that's exactly what we're saying in this condition, right? We're saying that for anything in the codomain, and in the codomain, the things we've got are pairs of morphisms, right? So for any F and G, from C to X and from C to Y, there is a unique H such that pi1h equals f and pi2h equals g. But now, linking this with generalized elements, if I look at the left-hand side of this bijection, if I look at this side, in the language of the generalized elements, these are generalized elements of that Hom set are generalized elements of x cross y. On the other hand, on the right-hand side, we have generalized elements of x, Cartesian product with generalized elements of y. So in the language of generalized elements, basically what we're saying is that product is an object whose generalized elements are ordered pairs of generalized elements of x and generalized elements of y. So in a way, we're kind of defining Cartesian product in the language of generalized elements. I would like this to make sense, so please do ask questions to fill some of the gaps that I might have left in the explanation.
Yeah, Zurab, can you maybe just repeat that? Are we kind of saying that the Cartesian product itself is a more kind of general kind of homomorphism, or?
So let's see first if we are through with the first step of the explanation, which was to remind you of this bijection. Are you comfortable with that one? I mean,
yeah.
talking about this bijection.
Yeah.
Sorry? Yeah, okay. Now, if we look at this bijection, if we look at the left-hand side of this bijection, and let me actually copy this out and put it separately so I can talk more elaborately about it. I'm going to copy this. Can I copy things here? Let me see how to do that. Actually not sure how to copy things. Maybe I'll just move it over here. There we go. And put this back there. Okay, so if I look at this left-hand side, what is this? This is the set of generalized elements of x cross y, isn't it? With C being the fixed object. So remember, in the definition of a generalized element, we need to have a fixed object C. So it's kind of a relative concept. For every C, we'll have a notion of a generalized element. That's how we can think of it. And now we've got a fixed C. And for that C, Hom C x cross y is the set of generalized elements of x cross y. Do you agree with that, Matt?
Yes. Yeah, I agree.
On the other hand, the right-hand side is the set of generalized elements of x multiplied by, in the sense of usual Cartesian product, multiplied by the set of generalized elements of y. Do you agree with that?
Yeah.
So then this bijection essentially tells us that x cross y is an object for which its generalized elements are ordered pairs of generalized elements of x and generalized elements of y.
Yeah.
That's the point I wanted to make.
Okay. Yeah, no, I see that.
Yeah. Yeah. So that the definition of product of objects is done in such a way that it allows us to see x cross y as a kind of generalized Cartesian product of x and y.
Cool.
And this is a very fundamental idea, which unfortunately does not dualize And there is a big fundamental reason for why it doesn't dualize. So what do I mean by that? So if we consider now the same philosophy for sum, if I take sum here and I want to kind of classify x plus y as maybe union of set of generalized elements of x and generalized elements of y, it doesn't work because the definition of sum says nothing about things going into the sum. It says about things going out from the sum, not into. And my generalized elements are defined as things going into objects. So while I still am able to kind of think of every generalized element of x by composing it with iota 1, I can think of f as living inside x plus y, and I can think of generalized element g of y living inside x plus y by composing g with iota 2, right? So I do have maps from hom cx to hom cx plus y, as well as from hom cy to hom cx plus y. I might have much more generalized elements of x plus y than those that came from either x or y. So it's not the case that for sum, that sum is not defined as the product where we can just think of this as some kind of disjoint union of elements of x and elements of y, because in the category of sets, that's what sum is. And we did remark this earlier that sum of two sets will be disjoint union of those sets. But in the language of generalized elements is not able to capture this phenomenon anymore. And the reason why, I mean, just an example to kind of show that it's not able to do that, we can just look at, again, at the category of matrices. If I've got in the category two objects, n and m and k, right? And here I have, as we know already, sum and product in the category of matrices are the same thing. So that, this, and this and that. Just by counting how many matrices we have in each direction, we can see that there must be more matrices of dimension n times m times k. So let me actually use a dot here for, sorry, I made a mistake here, right? I should have written plus, not in the category of matrices, sum and product are the same and they're given by plus, by addition of numbers. So how many n by k matrices we have? What is the size of hom kn in the category of matrices? How many matrices we have of that? Well, we don't, maybe we shouldn't even count them because there'll be infinitely many, because the entries of the matrices are real numbers. So that's not the right way of going about it. What we can instead do is to look at the shape of matrices that come, I mean, the shape of morphisms from k to n plus m that go via n or via m, and see that we don't get all of them. So if we remember the matrix here, do we remember what these are? Which matrix was I1 and which matrix was I2? So I1 needs to be a matrix with dimensions n plus m and n. And so I think it is the identity matrix. And then here we have zeros. And I2 would be zeros, and then identity matrix will be at the bottom part. So now when I compose some matrix A with I1, I will get a matrix of which shape? So I1 times A will equal. So it needs to be an n by k matrix, right? N by k matrix, so n rows and k columns. So because of the zero here, I'll have a bunch of zeros, right? Does anyone want to tell me what kind of matrix we'll get there?
Is it m plus n by k?
Yeah, actually, you're right. Yeah, so what I wrote there was wrong, but what will be exactly the shape of the matrix? What will be the entries of the matrix? Thanks for that. So A is a
A.
Yeah.
Is it just A? Yeah, 0.
Yeah, that's right. It will be that. And on the other side, if I had a matrix B and I composed B with iota 2, with I2, I would get a matrix of the shape 0B. But of course, we have much more n plus m by k matrices, namely all those where not everything downstairs or upstairs 0 have been missed by iota by I1A type of matrices and I2B type of matrices. So this illustrates that Hom Cx plus y can be much bigger than the union of Hom Cx and Hom Cy. Are you happy with that, Matt?
Yeah. Yeah, I'm happy.
So generalized elements do not work for sums as well as they do for products. Sums and products are, of course, very symmetric to each other. What does work for sums would be kind of co-generalized elements. So when arrows go out from your object instead of going into. So sum will have its own notion of co-generalized element. Product has its notion of generalized element, but they don't have the same notion of generalized element. This shows us kind of complexity of products and sums. So if I want to be able to easily work with products, then my working with sums will be complicated. But symmetrically, if I want to work easily with sums, my working with products will be complicated. So I cannot achieve that working with products and sums to be simple simultaneously. And behind this fact is a very deep mathematical phenomenon in number theory. So let's do a little bit of detour to number theory. In number theory, as you know, in number theory, we study natural numbers with plus and multiplication. And all the kind of difficult problems of number theory are those that are combining both plus and product. There is nothing difficult about a number system if I only used addition as my operation. Because in fact, in this case, the natural number system can be seen as a free monoid over one generator, which means we can think of it as the monoid of words. My pen is making some mess here. Monoid of words over alphabet that only has one stick in it. So we write each number by as many sticks as the number. So if the number is n, we think of n as a word that's made out of that single stick as a single letter, written next to each other and many times. Similarly, if I only care about multiplication, this is still monoid of words. In this case, we have infinitely many letters, and this will be all the prime numbers. 2, 3, 5, 7, and so on. So the words I can form using the prime numbers, but actually, this time, I will not care about commutativity. So, I mean, I actually want commutative words, and we call it C words. In the previous case, that it's also commutative, but because there's only one generator, being commutative or not gives the same result. By C word, I mean that the order in which these numbers are written next to each other as letters doesn't matter. So the word, for instance, 2, 3, 3, 5 is the same word as the word 3, 3, 5, 2. Just because one is obtained from the other by rearranging the letters. And the fact that numbers can be thought of in this way is, of course, goes back to the theorem that every number decomposes uniquely up to permutation into a product of prime numbers. So in this case, we've got 10 times 9, which is 90. So number 90 will be written as the word 2335, which we see as the same word as 3352. So mathematically, monoids of words are very, very simple objects. They're so simple that even someone who doesn't know any mathematics can comfortably use it, since, as we know, most of the language, well, not maybe most, but many of the standard languages of the world make use of the monoid of words. We put letters next to each other to form words, not in every language, by the way, but in many of the standard languages, that's how we do it. And people seem to be able to learn how to do that without any problem, even if they don't know much mathematics. So if natural numbers were interesting only from the point of view of one operation or the other, they're very simple entities. But once the two operations are combined, that's when the theory becomes really complex and leads to open problems that sometimes takes centuries to solve. Like, for instance, Fermat problem, where we wanted to know what are the integer solutions of this equality, which, as you see, it involves both multiplication and addition. So it is not possible to have a simple way of computing or working with plus and multiplication simultaneously. And that impossibility is also what is seen here at a much more abstract level of an arbitrary category, right? So what I spoke here would be in the context of the category of natural numbers, where product and sum, categorical product and sum, become the usual addition and multiplication of numbers. But even more abstractly, the same phenomenon persists. And of course, if it didn't, then if it was easy to work with these things abstractly, then in the concrete case, it would have been easy to work with them as well. And so that's the phenomenon, basically, that the generalized elements of product classify, allow us to see product as a Cartesian product. But on the other hand, the same generalized elements do not allow us to see sum as disjoint union. And that's kind of in the interaction of product and sum, that's where things will become complex and interesting also in a deep way, like problems of number theory are. However, there is also, nevertheless, there is a lot of interesting mathematics one can do just with one of them, not using the other. since we're dealing with more abstract categories than just numbers, there are still things that come up there, which in the case of the category of natural numbers would have trivialized, but they're not completely trivial. Let's see now, how does the notion of a generalized element interact with terminal object. So remember, the terminal object is empty product. And so since it interacts nicely with binary products, we expect that it will also interact nicely with the notion of a terminal object. So let's have a look at that. So recall the definition of a terminal object. It says that an object X is terminal if for any other object C that is unique morphism from C to X. Do you see this as a way to say that X has a unique generalized element? So in other words, that X is a singleton?
Yeah.
Great. So we're essentially saying that Hom CX here has cardinality 1. So seen as a kind of generalized set, X is a singleton. Of course, it matters here that each time when we talk about generalized elements, we must fix C in advance, because for a different C, there will be a different unique morphism. And F and G will not be the same. So this idea of reducing categorical constructions to sets by generalized elements only works when each time I fix my domain for generalized elements. Okay, great. So now what we're going to do, we're going to try to maybe prove a property of products that will make use of this generalized language philosophy as a way for us to transfer our experience of working with usual Cartesian products to this more abstract setting, and now being able to work with products of objects in a general category, thanks to the language of generalized elements. The property we will establish is that X cross Y by the way, would you like to have a short break, or should we keep going?
I'm happy to still go.
Okay, anytime anyone wants to have a short break, just let me know and we can pause a little bit. So we're going to establish that X cross Y is isomorphic to Y cross X. In set theory, of course, we know that Cartesian product is not commutative strictly, because there is a difference between ordered pair XY and ordered pair YX. They're not equal to each other. But if I map XY to YX, I get a bijection of Cartesian product X cross Y and Cartesian product Y cross X. And it is very easy to build this bijection by just the mapping I described, right? So to prove that X cross Y is bijective to Y cross X using usual sets, so to prove that for the category of sets, we do the following. We say, okay, define this map, XY mapping to YX. And to prove it's a bijection, I need also a reverse map. So I'll have a reverse map that will map some Y prime X prime. It will map each Y prime X prime to X prime Y prime. And now I need to check that these two maps are inverses of each other. So let's give them names. So one of the maps, we can call them F, and the other we can call G. So I'll have this map F. and backwards I'll have the map G. And I want to prove that GF is identity, and I can do that by applying it to an arbitrary element xy and computing the result. So it will be G applied to, what is f of xy? Well, that's yx, right? And what is G of yx? Well, that's xy. And so we get a GF of xy is the same as the identity function of xy, x cross y, applied to the pair xy. And because this is true for every element, GF and identity function need to be the same function. And in exactly the same way, we can prove that fg of yx will always be equal to yx. First apply g to yx, we get xy. And then applying f to xy, we get back yx. So we then get this the same as identity of y cross x applied to yx. So once again, fg then must equal to that identity function because they act the same way on elements. Okay, so we've got in front of us proof of the fact that x cross y is bijective to y cross x, but this proof is only valid in the category of sets because we made use of the internal elements of objects in this category. We want to externalize this this proof by switching from usual elements to generalized elements and see if we can maybe employ the same type of computations, but this time we want x and y to be generalized elements of capital X and capital Y. Let's see if we can do that. To help us with the generalization, I'm going to turn these computations into diagrams. So I've got my xy here, x cross y. And now I'm going to look at this ordered pair xy. And I actually want to think of it as a column because we did agree to write morphisms going into products as columns. So that's one change I would have to do in my notation, replace every row xy into column xy. And then as a column, it will be a generalized element of x cross y. So let's fix some object C, which is the domain, the common domain of x and y. But now I still need to define f and g first before I even do any computations with them, right? So using usual elements, f and g were defined this way, but now I need to define it using the definition of product of objects in a category. These things were defined by the way they act on elements, right? Let's see if maybe we can use that here also. So I need an f here, which acts on the column xy in the following way, that when I compose f with that, okay, now I realize that I didn't say something very important about how generalized elements interact with other morphisms. So we're going to make a little pause here, and I'm going to now fill in the gap that I left off. Let me do that on the side. I'm going to move to the right side here. If I have an object x and an object y, and a morphism f from x to y, and if I have a generalized element small x of capital X, what is the intuition behind the composite fx? In the case when this small x represents the actual element in the specific scenario where C is a singleton set, so small x identifies some element, let me call it x star, which is actually the function x applied to star. In this case, what does the composite fx do? Well, let's see. It should identify, so fx should identify the value of fx at the star, right? So fx star is equal to fx star, x applied to star is x star as a subscript, and f applied to that. So this is two functions are being composed, right? So we apply one function and then the other. F applied to that is just that. If it's f of x lower star. So you see that when x is a representation, is morphism representation of the element x star, the composite fx becomes morphism representation of the value of f at that x star. So basically what I'm trying to say is that intuitively, going back to the previous picture, we can think of fx as what we previously would have written as f applied to x. Does that make sense?
Yes.
So composition of functions now becomes also a way of evaluating function at an element. And this, by the way, has very important use in the category of Hilbert spaces, where we try to write out laws and some other formulas from physics in the language of morphisms of the category of Hilbert spaces. Okay, so with that concept in mind, let's go back here. And now let's think of this composite. F composed with column vector xy as the value of f at xy. And then we want that composite to equal, because we want f evaluated at the ordered pair xy, we want that to be yx, right? We want that to equal yx. So I'm looking for f that fulfills this property for every pair xy. I mean, for sets, we know we can define f just by saying define f of xy to equal yx. Here, I still need to make sure that such morphism f exists, so that f evaluated at the pair xy gives me yx. So I'll have to go back to the definition of product to figure out what is this f that can do that. There is fascinating additional tool we get when we switch from elements to generalized elements that is not available in the case of elements. And that's ability to fix a specific generalized element to carry out the definitions and proofs that we would like. In the category of sets, I would have had to prove, let's say, this formula for arbitrary pair xy. If I just prove for a single pair xy, it's not enough, because gf could be equal to identity a function for a single xy, but for a different xy, it might not be equal to that. But with the language of generalized elements, it turns out that very often it is sufficient to pick just one generalized element, and that is because we are able to fix various different domains for generalized elements. So not for a fixed C, but we can find a C so that for that specific C, choosing one generalized element is enough to do what we want to do. And in this case, we're going to choose that C to be x cross y itself. So I choose my C to be x cross y. I now need to choose generalized elements small x and small y, the unique one I will choose to do what I want to do as I promised. Okay, how do I choose them? Well, I'll take small x to be. Remember, if C is x cross y, then generalized element of x needs to be a morphism from there to x, and generalized element of y with that C needs to be a morphism here. And we have canonical morphisms from x cross y to both x and y, right? The one to x we have that we call pi1, and the one that we have to y, we call it pi2. We've got them given together with the definition of product. So let's choose them. Then we'll form here a column pi1, pi2. Now, this pair, which kind of appears to be a mysterious entity, is actually something that's very familiar for us because by definition of this middle arrow, remember that middle arrow is defined as a unique H, such that when I compose that with pi1, I recover the first component of the pair, in which case it's again the same pi1. And by composing that with pi2, I recover the second component of the pair, which is again pi2. So basically, the two triangles commute, right? That's what defines the horizontal map to be unique. But of course, we have a map from x plus y to x plus y, which does make both triangles commute. Which is that map? Which morphism here would make these two triangles commute? So I'm trying to reveal that this column actually needs to equal to something very familiar to us. And so let's try to discover what that familiar thing should be, because it's defined as a unique morphism that makes its triangles commute. If I find something familiar from x cross y to x cross y that does make those triangles commute, then that will have to equal to the other one by uniqueness of that H. So what is the most natural morphism from x cross y to x cross y? Think of that and then check if the triangles will commute or not. And remember, in category theory, every question is easy to answer. That's the whole philosophy of the subject. That's how it simplifies mathematics, by turning complicated things to easy stuff.
Is it the identity?
That's right. It's the identity. And so this column pi1, pi2 then must equal the identity. Right? Now, my morphism F that I'm looking for should be such, according to the diagram we have above, F should be such that this composite equals the other ordered pair, pi2, pi1, right? Okay, so now let's make sure we don't get confused between pi for the Cartesian product xy and pi for the Cartesian product yx. So let me write as a superscript to pi, which product are we working with, just for now, otherwise later on one drops the superscript, just for simplicity of notation. So this is the pi1 for x cross y. So we're going to draw that in everywhere. And that's the pi2 of x cross y. Now this one is also pi1 of x cross y. And here also x cross y. Here, on the other hand, we have pi1 of y cross x and pi2 of y cross x. And now we're told that the composite of f with pi1, pi2, which is identity morphism, so that composite is actually just f, right? So this composite now that goes from here to there will just be f, because the other one is identity. So f equals f composed with pi1, pi2, where again here these pi1 and pi2 were of x cross y. We want that, right? We want this composite here to equal yx, yeah? So we want that to equal the ordered pair pi2 x cross y pi1 x cross y. So we're looking for f, right? Remember previously we were looking for f such that for every small x, small y, f composed with the column xy is column yx. And this needs to happen for every small x and small y. So in particular, it needs to happen in this scenario where small x is pi1 and small y is pi2. So in this specific scenario, we're looking for f that composed with pi1, pi2 as a column as a column matrix is equal to pi2, pi1. Which is such f? Can we find such f? Again, remember every question in category theory is easy. So in mathematics, when you learn mathematics, you learn to solve difficult problems. Now, when you learn category theory, you must learn how to solve easy problems. So think easy and try to answer the question, can we find f such that f composed with pi1, pi2 will give pi2, pi1? And keep in mind that pi1, pi2 turned out to be identity morphism. Okay, maybe there was something here that you didn't quite understand or I didn't quite explain well. So if you want to ask me some questions before answering the question, feel free to do that. Okay, let me try to re-explain what we're doing, right? So going back to sets, we are trying to construct a bijection from x cross y to y cross x, and we defined it, this bijection f. Well, we later prove it's a bijection. We define f by saying that the pair xy must map to the pair yx, and that of course defines f uniquely. We want to transfer this idea to defining a morphism from x cross y to y cross x by saying that this morphism, when applied to generalized element xy, must give me generalized element yx. And we already know how we apply morphisms to generalized elements. That's just by composing them. So we want f composed with xy to equal yx. And we want f that fulfills this equality, no matter what c is, no matter what small x and small y are. We're looking for such f, such a universal f that will work for all c, x, y. And then I said after that, I said that, in fact, we will find such f for a specific c, x, y, and that's a specific f we will find that later we will prove it actually works universally as well. So the specific scenario of c, x, and y we are now looking at is the scenario where c is x cross y, small x is pi 1, and small y is pi 2. And I'm now referring to this pi 1 here and that pi 2 here. Okay, so for this specific scenario, what are we looking for? We're looking for f such that f composed with pi 1, pi 2, such that f composed with pi 1, pi 2 equals pi 2, pi 1, right? But in this scenario, pi 1, pi 2 ended up being identity morphism. So we're looking for f such that f composed with identity morphism gives us pi 1, pi 2, pi 1. Can we find such f?
So should f not just be pi 2, pi 1?
Exactly. Yeah, that's what f is.
Okay,
it was
cool.
easy, right?
Yeah.
Okay, fantastic. So we will basically, the criteria by which we were looking for f tells us what f should be. It should simply be this morphism, pi 2 x cross y and pi 1 of x cross y. It's kind of the twisting map, right? I mean, now maybe it's obvious that it should have been the case that it will twist the coordinates. So if I want to draw this out separately, just to clarify exactly what that is. So in column notation, it's what we wrote, but in terms of the explicit definition of the product has this property that giving morphisms to the to each of the x's gives us the morphism into the product. And so in this case, these morphisms are to the first component of the product, which is, I'm now talking about the right-hand side product, it's going to be pi 2, and to the second one is going to be pi 1. So this pair gives me unique morphism here, which is the one that we denote by column pi 2, pi 1. And I'm now not putting those superscripts anymore, just to make the notation a bit lighter. So we have a candidate for f. But remember now, we also want the other way around. We also want g, something that goes backwards, but g kind of does the same thing, right? It twists the coordinates again. So it's probably not difficult to see that the same kind of investigation would lead us to saying that the g here that we're looking for, so this is the f, the g must be defined in the same way, but now instead of the superscript xy, we'll have superscript yx. So here we'll take, again, pi 2, but this time it's the pi 2 of y cross x. Previously, it was pi 2 of x cross y. And here it will take pi 1. Once again, previously it was x cross y, but now it's y cross x. So this is going to be G. Pi 2, pi 1. It looks similar because we're not writing the superscripts, but remember superscripts should actually be there. So F and G are not the same morphism. They're defined similarly, but they're not the same. They're not identically the same morphisms, right? One goes from x, y to yx, and the other goes backwards. Okay, so well, earlier we said that if I find f that fulfills this equality here, that f composed with xy must be yx, then if I find that f for a specific c, specific small x and specific small y, then I'll be fine. We didn't prove that yet, that will be fine. But maybe we can skip over that because all we want is just an isomorphism from between xy and yx. We already have two morphisms going between them, f and g, and now I want to prove that their composites are identity morphisms. So I don't really need to fulfill this law. So I'll cut my way short, and I'm not going to prove that, although we could have proved that if we wanted to. And let's directly try to prove that the composites are equal. That, for instance, G composed with F equals, sorry, not the composites are equal, but the composites are equal to identity morphisms, right? G composed with X equals identity of X cross Y. Okay, so once again, we can kind of go back to this set theoretic proof we had with small x and small y. So one route would be to go back here and to this series of equalities we had, and to prove that we have this for every small x and small y, but actually to prove it just for one, namely, once again, pi 1, pi 2, which ends up being identity morphism, which then kind of reduces to proving it, proving explicitly what we said here. So if I put a column vector here, pi 1, pi 2, because we already know it's identity morphism, that equality will just reduce to this one. So we directly prove this one, in fact. So in this scenario, it's actually easier to work directly than with generalized elements, although generalized elements gave us an idea how to build the F or the G. Okay, so why is GF equal to the identity? Let's trace what's going on the diagram. We've got here G is defined as that column, pi 2, pi 1, and the pi 2 and the pi 1 are displayed there. Let's also insert the labels for the unlabeled arrows. So this one from yx to y is pi 1 of yx, y cross x. And the other one is pi 2 of y cross x. So, and on the other side, I've got here pi 1 of x cross y. And here I've got pi 2 of x cross y. And let's also put it on the diagram, the morphism we're trying to compare the composite with. So we've got this composite of dash arrows. This is the GF composite, right? And let me actually remove these brackets here around GF. And the other arrow we want to compare this with is the identity arrow. So let's put that one in. So identity arrow goes this way. So this is the identity arrow x cross y, which from previous discussions, we already know it equals pi1 x cross y and pi2 x cross y. So I've got two morphisms, right? Two potential morphisms from x cross y to x cross y. One of them is the identity morphism, and the other is the composite GF. So let's maybe kind of draw that separately here. I've got my x cross y. And I've got two morphisms. The composite GF and the identity morphism, which equals to that pi1, pi2, but I'm not going to write that now. When I have two morphisms going to the same product, we can think of this as kind of two generalized elements, right? But then because of this Cartesian nature of the product, the two morphisms would be equal if they had been equal after they are composed with the pi1 and pi2, right? So if I put pi1 here and pi2, if it turns out that both composites with pi1 gives me the same morphism there, and both of them with pi2 gives me the same morphism here, then by the definition of the product, these two morphisms must be the same, right? So that's what we're going to prove then, that these composites are the same. So let's calculate what is pi1 of x cross y composed with G, composed with F, and since this is since composition is associative, I can just write it down without brackets. And then look at the diagram here. I've got my morphism G from Y, so I'm gonna make it thicker now. Morphism G from Y cross X to X cross Y, which is defined as the column pi to pi1, right? Now, what does that mean that is defined as such a column? It means precisely that this G composed with pi1 xy, and I'm going to make that thicker as well. So the composite of these two arrows must be this arrow, the third one I'm making thick. That's what it means for G to be the column pi to pi1. In other words, what I'm trying to say is that this composite over here, pi1 xy composed with G, is equal to pi2 yx. And I still want to compose that with F. But we actually know what pi2 composed with F is, because pi2 is the same arrow as the one shown here. I'm making that bold as well. And as you see from the diagram, that composed with F is pi1 x plus y. It's this one. But now, notice what happened here. We did prove that the G compose F morphism composed with pi1, that's this one, right? We did prove that equals identity composed with pi1. Because, of course, I can write in the identity here, because identity doesn't change morphism. So they both equal to the same morphism. That's the one that would have been displayed here. Let's actually write this down. So pi1 GF, I'm now not writing the superscript anymore, equals pi1. And with a similar computation, I can also establish the other side, this side. It will be exactly the same kind of principle. On the diagram, the arrows we colored, we made thicker. Now, for the other proof, we will use the complementary ones, so the horizontal ones and these ones. So making them dashed, kind of thicker. So this will give us that pi2 composed with G composed with F equals pi2. And then because by the definition of the product, then these two morphisms, this one and that one, have to be the same. So the conclusion, we get that G composed with F must equal the identity. And exactly the same methodology will allow us to prove the other direction as well. We will be able to prove that F composed with G equals the other identity. Now, let's see if, because, so the proof now became very diagrammatic and kind of, it feels like it's complex, and indeed it is. If you don't draw these diagrams, then it will be very difficult to imagine this proof in your mind. But let's nevertheless see maybe if we can simplify this a little bit by going back to the language of generalized elements. So we kind of said that we don't need it, but maybe we can actually make use of it. So G composed with F applied to the generalized element pi1, pi2, which we know is the identity morphism, must equal to the identity morphism, which is pi1, pi2, right? So this now becomes a familiar equality where we're saying that the pair xy must map to the same pair xy by gf if gf is to be identity function. So what is g of f of? So first, let's see if we can compose f with pi1, pi2. Okay, so let's go back to the diagram. So, yes, you want to ask something?
Yeah, f of pi1, pi2 is pi2, pi1.
Yeah, that's a very correct guess. Let's try to see why is that so. Yeah, actually, you're right, because okay, maybe first things first. Let's kind of keep track of which pi1 this is. So this is x cross y pi1. Because f goes out from x cross y. And this is also x cross y pi1. So f was defined in a certain way, right? In fact, f was defined by saying that this must equal pi 2 pi 1. That's why you said it, right, Matt?
Yeah, but yeah, and this notation is like pi1 of y cross x.
Yeah, exactly.
Yeah.
Yeah. So we get G composed with pi2 y cross x. No, wait, something is wrong.
Yeah, isn't it pi1 of y cross x?
Let's see again. So here is our f, right? Where here is identity, where is f? I think it's pi2 x cross y, pi1 x cross y still. Not y cross x. You agree?
I'll need to check now again, but I would have thought that it's like g of pi1 y cross x, and then the second row pi2 of y cross x. But I'll double check now.
So do you know where I am on the screen? If you go back to when I scroll the screen, you don't see that, right?
Yeah, I see. Yeah. I see. Now I have to find you, but yeah, I think I'm there where you are now.
Mm-hmm. So you agree that f composed with pi1, pi2 gives pi2, pi1 with x cross y in the superscript.
Just one sec. F composed of pi1.
So I'm now going to circle the equation I'm using.
Oh, okay.
Which is also something we have here.
Yes. Okay. Now I agree with you now. Yeah.
Mm-hmm. So we have because f is supposed to twist the coordinates, so f cannot bring in some other superscript.
Yeah.
So this will still be x cross y here. And also this will be x cross y. Okay, what about g? Let's see what did we do with g. So g was defined in terms of pi2 of y cross x, not x cross y, right?
Yes.
So we don't really know how to compute this one, right? And it turns out that there will be a general principle, a kind of addition to our let me just check something quickly, sorry. Yeah. So what happens here is that basically we have a setup like this. So G goes from y cross x to x cross y, right? And this morphism here, pi 2, pi 1, is induced by, I'm going to now switch to kind of general notation. So if I had some C here, and I had morphisms going into y and into x, let's say small y and small x, this would give me a column yx. And now I need to compose that column with G. And the problem that arises here is that I'm actually myself a bit confused here. Why isn't this coming out from things we already discussed? So the thing is that when I look at the definition of x cross y, to know what this composite is, I need to know what it will be after first projection, right? And then what it will be after second projection. Do you agree with that?
Yeah.
And maybe that's what maybe that's what we should do. We should write this out as the corresponding column. So G itself is the column pi 2 x cross y. And here we have pi 1 x cross y. And I think the difficulty we are encountering here is the fact that now we are supposed to multiply two column vectors. We don't know how to do that. Sorry, the other one should have been y cross x.
I think it should be y cross x G.
Yeah, you're right. So we end up with something unnatural from our previous mathematical experience. We never had to multiply two column vectors. And right now I'm not able to explain this more naturally than the following, but it is possible that when I'll be editing the video, I will come up with a more natural explanation. I will insert it as a comment. So the best we can do at this stage is basically to do what we have to do, which means to take this whole composite and compose it with pi 1 and then compose it with pi 2 and then write down the column as a result. So basically what we already did in the other calculation. So if I compose this thing further with pi1, G composed with pi1 is going to give me pi2, right? And pi2 composed with yx. So this is going to be pi2 of y cross x. And pi2 composed with yx is going to give me x, which in our case is pi1 of x plus y. Remember that C was x plus y, and x was pi1 of that x plus y, whereas y was pi2. So this composite, whatever this composite is, right? Whatever this composite is, it's a column. It's a column that consists of the top entry of the column being this composite, right? And the bottom entry being this one. So that's what I'm doing now. I'm computing those two entries. The top entry is, as I said, this composite, which is the same as this composed with, sorry, this composed with that. And that ends up being the same as yx composed with pi2. So in other words, this composed with this. That's our pi2, just like we had before, right? It's the same thing, which ends up being pi1. In the same way here downstairs, we'll have pi2. Okay, now I remembered what is the more natural explanation. So there is this additional law that will work in categories, that if I have a morphism induced by Fg, and I compose from the right side with any morphism H, that will always equal Fh composed with Gh. H kind of multiplies in like as if it was a scalar. So this is the general law that we could have employed here. And indeed, if you take, so basically what we want to do now, our H is this matrix, and we want to multiply it in right here as well as right there. So let's actually do that. So I'm going to have, by this law, which can be confirmed separately, I'm going to have pi2 here. What is very bad about this whiteboard of Zoom is that it only shows what I wrote after it has updated on the other side, which makes writing quite cumbersome. With every stroke, it only shows when it's gone through. Next time, I'm not going to use this. So that matrix multiplies in both of the coordinates there. And then after that, it's just a matter of composing that ordered pair with pi2 and pi1, but they're just picking out the coordinates. So we will get exactly what we wanted to get. So pi2 composed with that thing there is going to be pi1, just like we wanted. So that's pi1 of x cross y. And the other one will be pi2. There we are. Learning this calculus of how to work with such composites in a general category is going to be useful for later on for us, because we would want to, I mean, if we do go in that direction, we want to translate, as I said before, we want to translate maybe some equations from physics in a categorical language, and in that process we will be doing these kinds of things. And so learning how the translation works and what are the added ingredients of the general category theoretic calculus will be useful. So now we would have proved here that, just to summarize, that GF composed with pi1, pi2 gives us pi1, pi2. And because pi1, pi2 is actually identity morphism, that's what we wanted to prove, right? We also showed it here. So we proved it in two different ways. We proved it using just the diagrams, and then we also can prove it using this algebraic manipulations, which kind of imitates what we do with sets and functions, except that there is this one additional rule, which we didn't have in the case of sets and functions, because remember there, f and g would be elements, and you cannot multiply element f with another element h or function h. Although this can be interpreted as f composed with x, right? This has no interpretation in set theory. X can do nothing with y because x is itself an element. So only when we multiply x on the left side, we can think of a function applied to x, but not the other way around. So because the elements here in the generalized elements are also morphisms, right? So they have this dual nature. They have the nature of being morphisms as well as being elements. And here in this magic equality, which is left as a homework to prove. So this is the homework. Homework is to prove this equality is true. In this equality, we are using double nature of f and g. So we want to think of them as elements because we're making ordered pair out of them, but we also want to think of them as morphisms because later on we are applying this element to H. Any questions?
Not from me.
Was the lecture followable, Matt?
Yeah, no, it was. I just got lost with the symbols in the end here, but if you just fall back to the diagram, then like it becomes clear again.
Right.
So
right.
And that's a nice way to look at the things.
Mm-hmm. Mm-hmm. Okay, then. So we will then stop here, and next lecture we'll probably continue working with generalized elements. and also perhaps introduce other kinds of limits as well. So products are special kinds of limits, as we already said previous time, but there is also other kinds of limits which are not products. They are called equalizers. We might introduce them, and it's a natural way of introducing them after we've already looked at what generalized elements are. By the way, the topic of generalized elements is something that's, on one hand, is extremely important tool for a working category theorist. On the other hand, you won't really find texts that elaborate on this tool. So it will be difficult for you to find the material we discussed in this lecture in other texts or other videos. And the same will probably apply for the next one. But anyway, so thanks a lot for being there, and we'll talk again next Saturday, which will also be an online lecture because I'm still away next Saturday as well.
Cool. Thanks, Zurab, and enjoy,
Thank you very much.
your
Thank you, Zurab.
and your journeys.
Thank you. Bye.
Bye.
Cheers.